Student, in the last class we discussed some properties of a linearly independent and dependent and proved some results. In this class today we some more results, and in the end we have to some examples, some different type of examples if we have to try to find the linearly independent and dependent. Okay, let's begin with the result. This if in a vector space V, if the set V1, V2, Vn is linearly independent, and if V does not belong to the span of V1, V2, Vn, then the set V, V1, V2, Vn is linearly dependent. Okay, so we have a given two things is there. So one is giving this is equal to V is not a span of this, and we also giving if set V1, V2, Vn are linearly independent. So that means we have a given this set V1, V2 up to Vn is linearly independent. That means that there's a linear combination of these vectors should be trivial, and this means we can write into the is a 0 vector, and this implies that alpha 1 is equal to alpha 2 is equal to alpha n is equal to 0. Now we have to prove that this set of vector is linearly independent, and this is we have a given. Also V does not belong to the span of a V1, V2 and Vn. So that means we can write this in the form of assuming that this set of vector is linearly dependent. So we have to assuming that the set V, V1, V2 up to Vn is linearly dependent. That means the linear combination of is alpha times V, comma alpha times V. We have a plus alpha times 1 V1 plus alpha 2 V2 and so on, plus alpha n Vn is equal to 0 vector. So if this is V0 vector, then we try to prove that at least one of them is not equal to 0. So where alpha I is the elements of R, because we have to working in the real field, scalars are the real number. So this means we can say that if this thing is equal to 0, because we are assuming this set is linearly dependent, so at least one of the alpha, alpha 1, alpha 2, alpha n is equal to 0. So this only possibility this alpha should be not equal to 0. Why? Because we have a only possibility is alpha should be not equal to 0. Why? Because if alpha 1, alpha 2, alpha n is equal to 0 is already we have a giving, because with the set of vectors V1, V2, Vn is a linearly independent. So if we linearly independent, then all the scalars R is equal to 0. So that means this set V1, V2, Vn, so only possibility is the alpha is not equal to 0, and this means this implies that 1 upon alpha is also belongs to the set of real number. So this means alpha of V can be written as a form of a minus alpha 1 V1 plus minus alpha 2 V2 and plus so on minus alpha n, and we have a Vn. Now alpha is not equal to 0, so 1 upon alpha is also is some scalar. So we have to multiply it both side 1 upon alpha. We have a alpha V, and this is equal to 1 upon alpha minus alpha 1 V1 plus 1 upon alpha minus alpha 2 V2 plus so on, and then in the end we can say that 1 upon alpha minus alpha n and Vn. And this means this can be written in the form of this 1 upon alpha into alpha V is equal to minus alpha 1 upon alpha V1, and this is equal to you have a V1, and then we have a plus minus alpha 2 upon alpha V2 and so on, plus ka minus alpha n upon alpha Vn. Because alpha 1, alpha 2, alpha n are also the real number. So this means this whole thing is belongs to the R, and this is whole thing is also belongs to the R, and this whole thing also belongs to the R, and we have this set is equal to 1. So this means this implies that we can write V can be written as a some beta 1 v1, beta 2 v2 and so on, beta n vn, where beta I is equal to minus ka alpha I upon alpha, and this means we can say that this beta v can be written as a finite linear combination of the elements of a v1, v2, vn, and if v can be written as a finite linear combination of the element of a v1, v2, vn, that means we say that v belongs to the span of, so we can say that this v belongs to the span of v1, v2 up to vn, and that means if v is belong to a contradiction, because we have given that v does not belong to the span of v1, v2, vn. That means we can say that we say that this is clearly contradiction. This means our assumption of set of this vectors are linearly dependent. This is linearly dependent is wrong. That means we can say that this implies that, hence we can say that the set v, v1, v2 up to vn is linearly independent. So this completes the proof of this result. So this means we can say this is true, means if v does not belong to the span of a v1, v2, vn, and v1, v2, vn is linearly independent, then the set v, v1, v2 up to vn is linearly independent. Okay, let's now we have to move to the this. We can say that if a set is a linearly independent, then any subset of it is also linearly independent. So that means we can say that in, if we have this as we have any linearly independent set and we take a subset of this is also is again is a linearly independent. So this we have to prove this. Let S is equal to, you have a v1, v2 up to vn be a linearly independent set. So we are assuming that one set is v1, v2, vn. If this is a linearly independent set, means we can say that the linear combination of these vectors is a trivial linear combination. Trivial linear combination means we have a alpha 1 v1 plus alpha 2 v2 plus so on, alpha vn is equal to 0, and this implies that if these vectors are linear, alpha 1 is equal to alpha 2 is equal to and so on is equal to alpha n is equal to 0. So in this case we can say that all alpha is equal to 0. Now we have to assume, now take any subset of this. Now we have to take any subset of S, say we can say that T is equal to v1, v2 up to vk, where k is less than n. So now we have to show that this v1, v2, vk is linearly independent. If we have to show that this set is linearly independent, means we can write the linear combination of this vector is only the trivial linear combination. That means if we have to write some scalar, so we have a beta 1 v1 plus beta 2 v2 plus so on, beta k vk is equal to 0. Now our objective is show that this beta 1, beta 2 and beta k are 0. So we have to show that this all this is equal to 0. Now this can be can be written in the form of this form, beta 1 v1 plus beta 2 v2 so on, beta 2 v, beta k vk plus 0 into we have a v of k plus 1 and plus so on, this is 0 into v of n. So this linear combination can be extended into this form. We can write beta 1 v1 beta 2 bk f plus 0 into this is because we have to adding this is 0 and this is equal to we have a 0 vector. So now we have a v1, v2, vn up to vk, vn is a linearly independent. Now we have to just say that this is equal to 0, but we have a given that the set v1, v2 up to vn is linearly independent, and that means if this is linearly independent, means if this linear combination is a 0 vector, and this set vectors are linear independent, then only possibilities is equal to beta 1 is equal to beta 2 and so on. We have a beta k, and then we have a b is equal to 0. So, we are assuming that this linear combination of a beta 1 beta 2 up to beta k is equal to 0 vector, and now we have to show that these scalars are 0. This implies that we can say that this T is linearly independent. So, this means we have to prove that if we have any subset of a linear independent set is again is a linearly independent. Now, if we take any superset, we have to subset. Now, if a set is linearly dependent, then any superset of a linearly dependent is also is a linear dependent. So, we have to take a superset of a linear dependent set. So, we have a like this, we have a any set, we have this set is a S is a linearly dependent, then we have to assuming that this is equal to is a superset, and this is equal to we have to assuming as a T, and that means we have to show that if this set is linear independent, and this means all the elements of this, again we have to try to find the this set is also is a linearly dependent. So, let we have to assuming that we have a given we have to take let S is equal to we have a V1 V2 up to Vn is be a linearly independent, be a linearly dependent set. Now, if it is linear dependent set, this means this implies that we have to write this linear combination alpha 1 V1 plus so on alpha n is equal to 0, and not all alphas are 0. Means if this set is a linear dependent, means at least this linear combination is equal to 0. If only not all 0, means at least one of the alpha is not equal to 0. So, now what we have to take any superset. Now, take any superset of S, say T is equal to V1, V2 up to Vn, and then we have a Vn plus 1 and so on up to Vm, and then we have to show that this T is also is a linearly dependent. So, that means if show that this T is also is a linearly dependent, means we take a linear combination of these vectors is equal to is again is a 0 vector, and implies that at least one of them alpha is not equal to 0. So, we write a linear combination alpha 1 V1 alpha 2 V2 plus so on plus alpha n and Vn plus 0 into V of n plus 1 plus so on plus 0 into Vm. We can write into this one. Trivially, we can write the linear combination of this again is a 0 vector. We write this linear combination of this vector is 0 vector, but you know that this all alpha not all alphas are is equal to 0, means at least one of them is non-zero. So, this means this is equal to 0, that means since not all alphas are 0, and means this implies that this is a we can say that this is a non trivial linear combination, and this implies that this T is linearly dependent. So, we have to complete this result. That means we can say that in this case we can say that if we have any set is linearly independent, then its subset is a linear independent. If any set is linear dependent, its superset is also is a linear dependent. Okay, so now we have to take any set. This theorem is very important theorem. We can just say that in this theorem we can say that in a vector space V, we have to assuming that V1, V2, Vn be an ordered set of vectors, and then we have to restriction is V1 should be not equal to 0. So, we can say that the set is linearly dependent if and only if one of the vectors, this is v1, v2, vn, suppose vk, belongs to the span of the all the preceding elements of this, means k, all the preceding elements v1, v2 up to vk minus 1. That is, vk belongs to the span of all these elements, where k running from n is equal to 2 to 3, because we have to assuming that v1 is not equal to 0. So means we can, there we have two types is this, we have a set is linearly dependent, then we say that one of the vectors of this can be written in the linear combination of the all the preceding vectors, or we have a, if vk is the element of a span of a this, then we can say that this set is a linearly dependent. So this is not, if is one way we can, very trivial, we can say that suppose we have a vk belongs to the span of v1, v2 up to vk minus 1. This implies that we can say that vk can be written as a finite linear combination of the elements of this alpha 1 v1 plus alpha 2 v2 plus so on alpha k vk minus 1. And that means we can say that this can be written in this form, and this implies that this can be written as 1 into vk plus minus alpha 1 v1 plus minus alpha 2 v2 and plus so on plus minus alpha and minus alpha k and vk minus 1 is equal to 0 vector. Now this set of a k elements, because if all the this is alpha are equal to 0, at least this is equal to, we have a non-zero element, 1 is not equal to 0. So this means 1 can be not equal to 0. This means this set, this implies that this set of these vectors, this implies that this set v1, v2 up to vk minus 1 and vk is linearly dependent. And because this is a subset, this is a subset of this, means any superset by the, we have to previous result, we proved that any superset of a linear dependent set is again linear dependent. So this means by the previous result we can say that v1, v2 up to vk minus 1, vk plus 1 up to vn is linearly dependent by the previous result, whatever we have to say into this form. Okay, so this means we have to assuming first, suppose the whatever proof is a span of this, then vk is a linear combination of v1, v2, vk minus 1. The set v1, v2, vk minus vk is linearly dependent, and just I have proved that. This means vk can be written in this form. So this means vk, I just said 1 of vk plus minus alpha 1 v1 plus so on minus alpha k minus 1, and then we have a vk minus 1 is equal to 0 vector. If all these are equal to 0 scalar, then at least this is not equal to 0 terms. So this means this set is linearly dependent, and this set is linear dependent, then any superset of this is also is a linearly dependent. So one way is very trivial. If we have to assuming that if v belongs to the span of a v1, v2, vk, then the set of v1, v2, vn is linearly dependent. Now conversely, we have to assuming that if v1, v2, vn is a linearly dependent, then we have to find elements, one of the elements x vk, which is belong to the span of a all the its preceding elements. The way of this proof we have to construct, we start from the one elements v1, and you know that because we have a elements v1 is not equal to 0. If we have a s1 is assuming that is a v1 and v1 is not equal to 0, that means clearly this set is a linearly independent. Now we have to prove that any non-zero vector singleton element in belong to the this set, this always is a linearly independent, because we have know that is equal to 0 into v is equal to 0. So this means see only v1 is not equal to 0, or we can say that other way, we can say that alpha v 1 can be is equal to 0, implies that either alpha is equal to 0 or v is equal to 0, but v is not equal to 0, the only possibility is equal to alpha is equal to 0, means this is a trivial linear combination. And this way we have to construct in this form. We choose another set S2, then we have a V1, V2, and then we have to construct S3. So let's start with, we have a, suppose this set is linearly dependent. So we have to construct a set S1 is equal to this. This is clearly is a linearly independent. Now we have to construct S2 is a this. Then similarly S3 we have to assuming this S3 means we have to apply this element V1, V2 and V3, and the similar fashion we have a S of I is equal to this, and similarly we have to Sn up to Sn is equal to V1, V2, Vn. Now our objective is we have to find a first linearly independent set, and then the first linearly independent set, and then by this if we have to choose a one linearly dependent set, and then linear, or this is linear independent is not a problem, this is linear independent. Now we move to the next, starting from this, if this is a linearly dependent set, this means V1 can be written as a scalar multiple of a V2. If we have to moving the where, that means we have to choosing the first linearly dependent set in this S1, S2, Sn. So S1 is a linearly independent by our assumption, and Sn is linearly dependent, we have also is given. So S1 is linearly independent because this is V1 is not equal to 0. So by the property of any non-zero vector is always is a linearly independent. And then we have a given condition, what this is Sn. Sn means V1, V2, Vn set is giving as a linearly dependent. So in this way we have to choose a go down the list, this list, and choose the first linearly dependent set. Suppose Vk, let Sk be the set, this first Sk is the linearly dependent. So if we have to going to down, that means we can say that Sk means we have a V1, V2 and then up to Vk. This is the set which is linearly dependent. That means if this is the set is a first set, this is the first linearly dependent set, means we can say that this implies that S of k minus 1 means we have a V1, V2 up to Vk minus 1 is linearly independent. Because we have to choosing in this case the first linearly dependent set, we say assuming that first Sk be the set which is linearly dependent, that means all the element of a previous Sk minus 1, Sk minus 1, Sk minus 2, others they are the linearly independent. So otherwise what is, if we have to, because linear, and we have to assuming that k lies between 2 to n, and since suppose Sk is linearly dependent, so we have a this is equal to 0, means at least one of the alpha is not equal to 0, means this is equal to, this means Sk is linearly dependent. So we can say that is, suppose one of the at least one of the alpha is not equal to 0, this surely this is the alpha k is not equal to 0 here, this is the only vector, this is not equal to 0. Why? If we have to change alpha k is equal to 0, then Sk minus 1 will become the linearly dependent. So if we have a, because all the elements of a previous we have to, this means Sk minus 1 is a linearly independent. So that's why we can say that if this set is if S11 is this is scalar is this is equal to 0, that means the previous element what is alpha k minus 1 Vk minus 1, and then because this set is equal to 0, so this means this set completely set is linearly independent, which is a contradiction. So would be this Sk would be becomes a linearly minus 1 linearly dependent set, contradicting our statement that Sk is the first linearly dependent set. Okay, so now we have to, if this is equal to Sk is the first, then means this is the non-zero vector. This means Vk can be written as a minus alpha 1 upon which, so this means we can write in the form of this alpha k and Vk, because alpha k is not equal to 0. So this way we can write the alpha k Vk is equal to minus ka alpha 1 V1 and so on minus ka alpha k minus 1 Vk minus 1, because alpha k is not equal to 0 and this is belongs to the R. So this implies that we can say that 1 upon alpha k, all those are element of a R. and in this case we can say that we have to this can be written as a 1 upon alpha k and alpha k v k and minus alpha 1 alpha k v 1 and so on. We have to write is a minus alpha k minus 1 v of alpha k minus 1 over alpha k v of k minus 1, and this is giving you an identity element is equal to 1 into v k is equal to this. It means v k 1 into v k is equal to you have a v k. So, this means v k can be written as a finite linear combination of the elements of a this is not 0 sorry. So, v k can be written as a finite linear combination of the elements of a this. So, which means that this v k belongs to the span of a this means this thing. So, this way we have to complete the proof of a this theorem. This way we can say that we have any vector which can be belongs to the span of as v1 v2 vk minus 1, then the set of vectors v1 v2 vk minus vk is linearly dependent. Okay, so now we have a by this example. So, I just write into this form is equal to S1. We have a write a 1 1 0 vector. Now, we have to start is equal to S2. Sorry, we have to write this. We have to start from S1 is equal to we have a 1 1 0, and now we have to start S2 is equal to 1 1 0, and we have a 0 1 1. Now, we have a S3 is equal to we have a 1 1 0. Now, we have a 0 1 1, and then we have a 1 0 minus 1, and now we have a S4 is equal to we have a 1 1 0 0 1 1. Now, 1 0 minus 1, and then you have a 1 1 1. Is these vectors are there? That means we have to this clearly is a linearly independent. This S1 is a linearly independent because this is a non-zero 1 1 0 is a clearly non-zero vector. Every non-zero vector is always is a linearly independent. Now, this is S2 is also is a linearly independent. Why is linearly independent? Because none of the vectors can be written as a scalar multiple of a other. So, we cannot write one of the scalar multiple of a other. So, we can say that here this S2 is also is a linearly independent. Now, we to try to check is this is equal to linearly S3 is linearly independent or dependent. Now, we can say that 1 0 minus 1 can be written as the 1 into 1 1 0 and plus minus 1 times 0 1 1. Now, this can be see this one can be written as a 1, this can be written as a you have a 1 plus 0 is equal to 1, 1 minus 1 is equal to 0. So, this means clearly you can just say that if we take a as this one sum of these two vectors is again is giving you a this vector, that means this is giving the 1 0 minus 1 is the belongs to the span of 1 1 0, and we have a 0 1 1. This means this vector can be written as a finite linear combination of the vectors of a 1 1 0 and 0 1 1. This implies that we can say that this S3 is clearly S3 is linearly dependent set. If S3 is a linearly dependent set, means any superset of this means S4 is equal to linearly dependent. So, we can say that S4 is also is a linearly dependent. We know that any superset of a linearly dependent set is again is a linearly dependent. So, we can easily by the previous theorem we have to if we have to check the linearly independent and dependent, we start from a single element and then we extend write a next element, adding next element. If one of the vector means this vector is not belong to the span of this. So, we have a clearly 0 1 1 is does not belong to the span of 1 1 0 because this can be not written as a scalar multiple of a this vector. So, in this way we can say that clearly these vectors form a linearly dependent. Okay, so now I have this problem. If we have a u, v and w be three linearly independent vectors, we have to prove or disprove that that u plus v, v plus w and w plus u is linearly independent or dependent. We have a given, what is the given? We have a given, this is vector is equal to, we have a given is a u, v, w is a 3 vector is linearly independent. That means that's a linear combination of alpha 1 u plus alpha 2 v plus alpha 3 w is equal to 0 always implies that alpha 1 is equal to alpha 2 is equal to alpha 3 is equal to 0. Now, we have to prove that these 3 vectors is linearly independent or dependent. We assuming that they are written as a linear combination of the elements of this. So, we write as equal to, we have to write in the form of this. So, we have to write alpha 1 times u plus v, and here we take it as different, no problem, beta 1 plus beta 2 v plus w plus beta 3 is u plus is a w plus u. Now, this implies that this is equal to 0 vector. Now, what we do, we have to, because u, v are the vector, by the property distributive property, this can be written as a beta 1 u plus beta 1 v plus beta 2 v plus beta 2 w plus beta 3 w plus beta 3 u is equal to 0. Now, this can be rearranging in this, we can write beta 1 plus beta 3 is equal to u plus beta 1 plus beta 2 v beta 2 beta 3 w is equal to is a 0 vector. Now, this can be written in the, but u, v, w are linearly independent. We have a given u, v, w are linearly independent. If u, v are linearly independent, then the scalars r is equal to 0. So, this means we can say that we have some scalars, because this is some real number, is some real number, some real number. We have to assume this is a gamma times of a u plus, we take a suppose alpha 1 u plus alpha 2 v plus alpha 3 w, where alpha 1 is equal to, you have a beta 1 plus beta 3, alpha 2 is equal to, you have a beta 1 plus beta 2, alpha 3 is equal to, you have a beta 2 plus beta 3. So, this means, but this is equal to, clearly this is the some scalars, because this is the element of a r, this is the element of a r, this is the element of a r, and by the this vector u, v, w are linearly independent, then the corresponding scalars r is equal to 0. So, this implies that all beta 1, beta 2, beta 3 is equal to 0, and this means that all beta 1, beta 2, beta 3 is equal to 0, means we can say that this scalars r is equal to 0. So, we can say that we have a beta 1 plus beta 3 is equal to beta 1 plus beta 3 is equal to 0, beta 1 plus beta 2 is equal to 0, we have a beta 2 plus beta 3 is equal to 0. So, we can write by these two, we can say that beta 1 minus beta 2 is equal to 0, and we have a beta 1 plus beta 2 is equal to 0, implies that beta 1 is equal to 0, then beta 2 0, then beta 3 0, then all scalars are 0. So, we can say that corresponding scalars are 0, means that these sets u plus v, v plus w and w plus u is also a linearly independent. So, I have to stop this lecture here, and in the next class we start the concept of a basis, and then we check how we set is this defined as a basis. Thank you very much.